So here we go with a little bit more review before chapter 16 and 17. First area we're going to look at some things from chapter 8, a little review of something called electronegativity. Electronegativity is the ability of an atom in a molecule to attract electrons. So it's how attractive these atoms are. And if you look on page 310 of the 13th edition, you can see that electronegativity increases to the right and it increases up, with fluorine being the Tyrannosaurus rex of the elements, being the one that wants to eat electrons the most. And so on your notes, you can just put a little arrow going this way. You can put F up here, and if you want to draw an F fluorine monster right here, you can. Give him some teeth, give him an eyeball, and you can know that he's the one that wants to eat electrons the most, and he's the most attractive to electrons on the periodic table. So it's a rating scale. It tells us how much things want to attract electrons to itself. Hydrogen is attracted to fluorine because it's going to give its electron away to fluorine, and this attraction is called a polar bond. Polar bond, remember, means that there is a dipole, and the dipole means that there's a more positive charge over here on this side, a more negative charge over here on this side to the thing that attracted electrons the most because it pulled electrons closer to itself. This molecule, or this bond, is then said to be polarized because it has a polar nature to it, two poles, one positive and one negative. Well, this makes a difference in acids, because in acids we want an H bonded to some nonmetal. And this H, of course, is donated in acids or given away. And the ability of the nonmetal to hang on to the H decides how strong or weak the acid is. So how polar is this bond? Well, here's a little rating scale that you can write down. First of all, very polar, middle polar, not much polar, no polar at all. And so HF would be one that sticks together really, really well because there's a large difference in electronegativity. And then moving to the right, you'd have HO, HCl, HBr, HI. These somewhat depend on what the O is connected to in the molecule. So I drew some little dots right here because it depends on the electronegativity of the next atom. But obviously, this is a pretty polar bond. Pretty polar, sort of polar, sort of polar. And anyway, these form strong acids, usually, not always. And the reason they do that is because they stick together pretty well, but not super good like this, and therefore they're able to donate or give away that hydrogen. Ones that aren't very much polar would be things like H connected to a C, which is of course a nonmetal that's pretty far over on the periodic table as far as nonmetals go. And then H connected to an H itself, a nonmetal to a nonmetal. This would be no polar at all. And these don't split and these don't donate. That's why you'll never see CH right here being the acidic proton or the hydrogen that's being given away. So we got to review some drawing of electron structures, or some drawing of some Lewis electron dot structures, because your ability to draw these types of things and determine how polar the bond is helps you decide lots of things about acids. So here's just a quick summary once again on how to draw Lewis electron dot structures. Sum of the valence electrons. The least electronegative atom goes in the middle. Carbon if you can, because remember carbon always wants to form 4 bonds. Bond everything else around it, and then make sure that that you add the unshared pairs of electrons to make everything have an octet, except for hydrogen, of course. Remember, hydrogen only wants a duet. It only has 1 electron, and so it only wants to end up looking like helium. Double or triple bond if it's not enough. And then here's some good hints on the next page for acids and bases. In this video cast, we'll just look at acids. The next one we'll look at bases. So like I said before, acids have a hydrogen, and they're connected to some nonmetal Z, depending on how many things are in the structure. If possible, the H connects to an O, but it doesn't always do this. But in like HClO2, an oxy acid, it's deceptive in the way that it's written And this is where this rule comes in, that if H can connect to an O, go ahead and do that. So let's go through drawing the Lewis electron dot structure for this. Add up the valence electrons, 1 for hydrogen, 7 for chlorine. Remember, chlorine right here is in the 17th column. Oxygen is 6, because it's in the 6th column, or the 16th. Multiply that by 2, and there's a total of 20 electrons. Put the least electronegative atom in the middle, which in this case would be chlorine, and then bond the other items around it. And now here's where the trick comes in, because a lot of people just look at this and say, oh, the H is going to connect to the Cl. But since it's an acid, if the H can connect to an O in an oxy acid, it will. And so it ends up looking like this, where the H connects to one of the O's. You can pick, it doesn't matter. And then complete the octets for everything. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons. And this is our acidic hydrogen, or the one that's going to be given away. So if you see an acid, HClO2, HClO3, HClO4, HClO, remember we called HClO3 and 4, the acidic hydrogen is always going to be connected to an oxygen. Bond this H to an O. This H is called the acidic proton. Well, let's get down to the meat of it here for a second about acids and bases. Acids are proton donors. They're H plus donors. And we know 7 strong acids: Hyber, Hickel, Hi, Hono, Hickelo, H2SO4. And of these strong acids, 4 of them are oxy acids, and so are going to have an H connected to an O in their Lewis electron dot structure. They're strong acids, and so they're really good donators of hydrogens. They have complete separation, aka ionization, aka dissociation. They split up lots. They completely dissociate when they're put into water. So here's an example. Here's HCl reacting with water, a strong acid, giving away a hydrogen to water. All the hydrogens from this HCl are given away to HOH. It becomes H3O plus right here. And then what's left over of the HCl after it releases its proton is over here on the right-hand side. So acids are things that give away or donate protons. Acids with carbons in it are known as organic acids lots of times, not always, but lots of times. And these organic acids, as you learned in the video cast before, always have a C double bond O, OH, COOH, or COO. The carboxylic acid group right here has the acidic hydrogen connected to the oxygen. And since carbon is just a little less electronegative than something like chlorine or nitrogen or sulfur, it's more difficult for this hydrogen to be given away. And so organic acids are 99% of the time weak acids. They give away this H, but with a little bit less gusto, not quite as much as these strong acids do. Here's an example of propanoic acid. Let's talk about drawing the Lewis electron dot structure for this. So it gives us lots of hints in the structural formula. We've got CH3, so we'll write that with carbon in the middle, CH3. CH2 connected to it, so CH with 2 H's on it, and then COOH, the C double bond O, OH. So the C double bond O and then the OH right here. And this would be the acidic proton, or the hydrogen that would be given away in its acid formula. Tune in next to learn more about drawing bases.